Welcome to the first part of Lesson 5. In this lesson, we'll explore how the three-dimensional arrangement of atoms within molecules affects their chemical properties and reactions. This is the study of stereochemistry, which involves examining the spatial arrangement of atoms in molecules and how these arrangements influence their properties. Stereochemistry is a fundamental aspect of our understanding of chemical structure, and we will see how these concepts play a vital role in nature and medicine. Let's go to the next page and look at the outline of topics before we get started. Here's what we'll cover in this lesson. The lesson is broken down into 3 parts. In Part 1, we'll start with an introduction and review the concept of isomerism. Then, we'll explore stereoisomerism, including symmetry and chirality, identifying chiral centers, and the concept of enantiomers. We'll also learn how to classify different types of stereoisomers. In Part 2, we'll learn how to assign R and S designations with an overview and step-by-step process, and discuss mesocompounds. Finally, we'll look at optical activity, including how it's measured, what it means, and conclude with a discussion on racemic mixtures. Ready to get started? Great! Let's go to the next page, where we will begin with a review of isomers. Let's take a moment to review the concept of isomers. What exactly are isomers? Fundamentally, isomers are compounds that have the same chemical formula, but are different compounds. Even though they are made of the same number and types of atoms, they have different properties and are not the same compound. Think of it like a set of Lego bricks. Suppose you use the same set of bricks to build 2 different structures. Although both structures are made from the same pieces, their different arrangements make them distinct from each other. Similarly, isomers have the same molecular formula, but are arranged differently, resulting in different compounds. So if isomers are different compounds made of the same stuff, what exactly is different about them? To answer that question, we need to look in detail at the different types of isomers that can exist. There are 2 general types of isomers. First, we have constitutional isomers. Constitutional isomers have the same molecular formula, as all isomers do, but they differ in how their atoms are connected to each other. For example, consider the 2 structures shown here. Both have the same number of carbons and hydrogens, but their connectivity differs, making them distinct compounds with different names, properties, and uses. Constitutional isomers, however, are not the only type of isomer. The second type of isomers are stereoisomers. Stereoisomers also have the same molecular formula, but they also have the same connectivity. So if they have the same formula and connectivity, what exactly is different about them? Stereoisomers differ from each other in a very special and sometimes subtle way: the spatial arrangement of their atoms. For instance, compare the 2 structures below. These 2 structures have the same formula and connectivity, so we know they cannot be constitutional isomers. However, we can see that these molecules are different from one another. How are they different? By the positioning of their atoms in space. If we try to superimpose one on top of the other, we would see that their atoms do not match up. This concept of superimposing molecules to see if they match is a key tool we use to identify different types of isomers. These molecules differ only in their arrangement in space, placing them in the category of stereoisomers. Soon, we will see that these 2 molecules are just one type of stereoisomer. There are others, and we will learn to identify and distinguish between them. Before we get into the technical details of stereoisomerism, let's first go to the next page and learn a little about the context of stereochemistry. We will look at how this phenomenon was discovered and its implications for modern medicine. Let's take a moment to understand how the concept of stereochemistry was first discovered. The story begins with Louis Pasteur, a renowned French scientist known for his groundbreaking work in microbiology and chemistry. In the mid-19th century, Pasteur was studying the crystals found in wine. He observed that the crystals of tartaric acid salts could be divided into two distinct shapes. These shapes were mirror images of each other, much like our left and right hands. Intrigued by this discovery, Pasteur painstakingly separated these crystals by hand using tweezers. Pasteur then discovered that these mirror image crystals had different optical properties. They rotated plane polarized light in opposite directions. This surprising observation led him to propose the concept of isomerism, where molecules with the same chemical formula can exist in different forms due to their spatial arrangement. However, Pasteur's theory about the existence of molecular asymmetry wasn't confirmed until 25 years later, highlighting the groundbreaking nature of his discovery. His work laid the foundation for the field of stereochemistry, which we continue to explore and expand upon today. Pasteur's meticulous work with tartaric acid crystals remains a classic example of how careful observation and persistence can lead to major scientific breakthroughs. As we will see throughout the course, understanding stereochemistry is crucial in modern medicine, and one of the most significant examples highlighting its importance is the case of thalidomide and Dr. Francis Kelsey. In the late 1950s, thalidomide was developed as a sedative and was later found to alleviate symptoms of morning sickness in pregnant women. By 1960, it was marketed in 46 countries. However, by 1961, severe birth defects were observed in children born to women who had taken thalidomide during pregnancy. These birth defects were devastating, with most cases occurring in Europe. The reason behind this tragedy lies in the stereochemistry of thalidomide. Thalidomide exists in two enantiomeric forms. One form is a sedative, while the other is teratogenic, meaning it causes birth defects. The mixture of these enantiomers in the drug led to its harmful effects. In the United States, this tragedy was averted thanks to Dr. Francis Kelsey, a pharmacologist working at the FDA. Despite immense pressure from pharmaceutical companies, Dr. Kelsey refused to approve thalidomide for market due to insufficient safety data. Her insistence on rigorous testing and caution saved countless lives. Dr. Kelsey's actions highlighted the critical importance of understanding stereochemistry. Her efforts led to stricter drug regulations and enhanced the FDA's oversight on new drug approvals. This case underscores how a deep understanding of molecular structure and its implications can prevent disasters and save lives. Let's turn our attention back to isomers for a moment and do a little practice distinguishing between stereoisomers and constitutional isomers on the next page. Let's practice distinguishing between different types of isomers. On this slide, you see several pairs of molecules. Your task is to identify each pair as either constitutional isomers, stereoisomers, or identical structures. As a brief reminder, recall the difference between constitutional and stereoisomers. Constitutional isomers have the same molecular formula, but differ in the connectivity of their atoms. Stereoisomers, on the other hand, have the same molecular formula and the same connectivity of their atoms, but differ in the spatial arrangement of these atoms. Please pause the video now and take a few minutes to analyze each pair. Try to determine whether the molecules in each pair are constitutional isomers, which differ in connectivity, stereoisomers, which differ in spatial arrangement but have the same connectivity, or identical structures, which are exactly the same. Once you've finished, unpause the video and we will discuss the solutions together. Welcome back. Let's go through each pair and identify the type of isomerism. Let's start with the top left pair. Notice that both molecules have a 6-membered ring and a single bond to a hydroxyl substituent. This tells us they have the same composition, meaning they have the same chemical formula, and they also have the same connectivity. This rules out constitutional isomers, leaving us with either identical structures or stereoisomers. At first glance, it might seem they are stereoisomers because the hydroxyl groups appear to be oriented differently in space. However, upon closer examination, we see that the hydroxyl group is in the equatorial up position on the first structure, and in the axial up position on the second structure. These are simply chair conformers of the same molecule and therefore identical. One can convert into the other through bond rotations, which are constantly occurring in solution. Moving to the right, we have the following two molecules to compare. We should first establish if they have the same connectivity. One way to do this is to derive the name for each molecule. We see that both molecules have a 4-carbon parent chain, with a double bond between the second and third carbon. This means that each molecule has a name that includes 2-butene. Each molecule also has a single methyl substituent. When numbering correctly, we see that the methyl group is on carbon number 2 in each case. So we see that these molecules have the same connectivity and composition, as they both have the name 2-methyl-2-butene. This rules out the possibility that they are constitutional isomers, so they are either identical or stereoisomers. Notice that the structure on the left has the same spatial arrangement of atoms as the structure on the right. Both structures feature 2 methyl groups on the same side of a double bond, and a single methyl group on the other. Also, notice you can simply rotate or flip one of the structures to make it look exactly like the structure on the left. This indicates they are identical. Moving down to the second row, we have 2 chair structures again. The connectivity in both molecules is the same, as we see the 2 hydroxyl groups are attached to adjacent carbon atoms of the ring. Are these identical or stereoisomers? Notice that if we classify the bond directions in each chair structure, the first structure has hydroxyl groups on up bonds, one equatorial and one axial. The second structure, however, has an up axial and a down axial. These two structures cannot convert into one another by a chair conformational change. They are different compounds by virtue of the hydroxyl groups pointing to different places in space. This means they are stereoisomers of each other. We can also see this if we convert the chair structures into flat wedge and dash style drawings. On one structure we have 2 wedge bonds because the hydroxyl groups are up, but on the other drawing, we have a wedge and a dash bond. These are not superimposable on each other, and are therefore different, not by connectivity but by spatial arrangements. Moving over to the next example, we can start by assigning a parent name and suffix for each compound. There are 5 carbon atoms in each, with a double bond starting at carbon atom 2, and neither has any substituents, so the base name for each is 2-pentene. But are these compounds the same? That's right, they are not the same. These two compounds differ by the spatial arrangements around the double bond. The structure on the left has the methyl group and the ethyl group on opposite sides of the double bond. The structure on the right, however, has these two groups on the same side of the double bond. These are stereoisomers. Great job analyzing these pairs. Understanding how to identify different types of isomers is crucial for mastering stereochemistry. Let's move on to the next topic, chirality, which starts on the next page. Now that we understand the concept of a stereoisomer, it is time for us to go a little deeper, and our first step is to learn about the concept of chirality. Chirality is a property of an object, or a molecule, that makes it non-superimposable on its mirror image. This means that no matter how you rotate or flip the molecule, it cannot be perfectly aligned with its mirror image. Objects and molecules are either chiral or achiral. Achiral is the word we use to describe something that is not chiral. An achiral object or molecule is superimposable on its mirror image, while a chiral molecule or object is not superimposable on its mirror image. The term chirality comes from the Greek word for hand, reflecting the idea that left and right hands are mirror images but not identical. Your hands are good examples of chirality, as they are mirror images of each other, but they are not superimposable. There are many examples of everyday objects that have this property, called chirality, that makes them non-superimposable with their mirror image. For example, most screws have chiral threads. Right-handed screws tighten clockwise, while left-handed screws tighten counterclockwise. Another example are scissors. Some scissors are designed specifically for right-handed or left-handed use. The blades are oriented differently, making them chiral. Many objects are achiral. A standard nail, for example, is completely superimposable on its mirror image, and so therefore is achiral. Let's turn our attention back to molecules. Molecules can be chiral or achiral. One of the most important features of many chiral molecules is that they possess a structural feature known as a chirality center. A chirality center, also known as a chiral center or stereocenter, is a specific atom within a molecule that has a unique arrangement of groups attached to it, leading to the phenomenon of chirality. Typically, this atom is a carbon atom, bonded to 4 different groups or atoms. The presence of these 4 distinct groups prevents the molecule from being superimposable on its mirror image, resulting in 2 non-identical mirror image forms, called enantiomers, that we will look at in detail on subsequent slides. For now, we want to be able to understand and locate chirality centers within molecules. Let's take a closer look at the example structures below and identify the chiral center in each. In the first example, we see that carbon atom 2 is bonded to 4 different groups: a chlorine atom, a hydrogen atom, and 2 different alkyl groups. This is an important distinction. While this carbon is bonded to 2 carbon atoms, we don't just consider the atoms, but the entire group of atoms that are connected. So we have a methyl group on one side and an ethyl group on the other. This specific arrangement makes this carbon atom a chiral center because it has 4 distinct groups attached to it, making the molecule non-superimposable on its mirror image. In the second example, the molecule features a carbon atom bonded to a hydroxyl group, a hydrogen atom, and 2 different alkyl groups. This carbon is also a chiral center because each of the 4 groups attached to it is different. The presence of these 4 unique substituents at the carbon atom means the molecule has a non-superimposable mirror image, illustrating chirality. The third example shows a ring structure with a carbon atom bonded to a bromine atom, a hydrogen atom, and two different groups within the ring. Here, the carbon atom in the ring, which is bonded to the bromine and the hydrogen, along with two different parts of the ring, acts as a chiral center. The specific configuration of these groups around the carbon creates a point of asymmetry, leading to chirality. In each of these examples, the carbon atoms are bonded to four distinct groups, making them chiral centers. This unique arrangement ensures that the molecules cannot be superimposed on their mirror images, which is a defining characteristic of chirality. All of these examples have exactly one chiral center, but many molecules have multiple chiral centers. There is an important relationship between the number of chiral centers and the total number of stereoisomers that can exist for a molecule. The formula shown below expresses this relationship. If a molecule has n chiral centers, then the total number of stereoisomers is 2 to the power of n. This means that a molecule with one chiral center can have 2 stereoisomers, while a molecule with 2 chiral centers can have 4 stereoisomers, and so on. An excellent question at this point would be, why does the presence of 4 different groups on an atom cause chirality to occur? The answer lies in symmetry. Let's go to the next page and explore this concept. Chirality most often results when a carbon atom is bonded to 4 unique groups of atoms. But why does this cause chirality? To understand this, let's examine the structures shown on the slide and discuss the concept of a plane of symmetry. A plane of symmetry is an imaginary plane that divides a molecule into 2 equal halves that are mirror images of each other. If a molecule has such a plane, it is considered achiral because it can be superimposed on its mirror image. Let's look at some examples shown below. Some of these example molecules have a plane of symmetry, and others do not. Look carefully at each. You are also strongly encouraged to build each example and its mirror image with your model kit. Seeing this phenomenon with a physical model is extremely beneficial. First, consider a molecule with a plane of symmetry, such as CH3X. In this molecule, the carbon is bonded to 3 hydrogen atoms and 1 X group. If you draw a plane through the carbon atom and the X group, it divides the molecule into 2 halves that are mirror images of each other. Because these halves are identical, you can superimpose the molecule on its mirror image. This means the molecule is achiral, as it does not have a unique 3-dimensional shape that distinguishes it from its mirror image. Next, look at the molecule CH2XY. This molecule has a carbon atom bonded to 2 hydrogen atoms, 1 X group and 1 Y group. Again, there is a plane of symmetry that divides the molecule into 2 equal halves, each being a mirror image of the other. When you try to superimpose this molecule on its mirror image, you will find that it aligns perfectly, indicating it is also achiral. Now, let's consider a molecule with a carbon atom bonded to 4 different groups, represented as CHXYZ. This molecule has no plane of symmetry, because all 4 groups are unique. When you look at its mirror image, you'll see that it is not superimposable on the original molecule. To understand this better, imagine trying to align this molecule with its mirror image. No matter how you rotate or flip the mirror image, you will not be able to make it identical to the original molecule. For instance, if you place the hydrogen in the same position on both the original and the mirror image, the other 3 groups, X, Y, and Z, will not align correctly. One group will always be in the wrong position, and this non-superimposability is what defines chirality. This lack of superimposability means that the molecule and its mirror image are distinct entities, known as enantiomers. Each enantiomer has unique spatial arrangements of its atoms, leading to different interactions with other chiral molecules. This difference is crucial in many biological processes and chemical reactions, where the 3D arrangement of atoms can influence the behavior and function of molecules. So, With 4 unique groups attached, the carbon has no plane of symmetry, and therefore exhibits chirality. Understanding this concept helps us appreciate why molecules with chiral centers behave differently and have unique interactions based on their three-dimensional shapes. Now that we have discussed the symmetry aspects of chiral centers, let's turn to the next page and practice identifying chiral centers in some slightly more complex molecules. Now, let's put our understanding of chiral centers into practice. On this slide, we have 4 different molecules. Your task is to identify how many chiral centers each molecule contains. Please pause the video now and take a few minutes to analyze each molecule. Look for carbon atoms that are bonded to 4 distinct groups, as these are your chiral centers. Once you've finished, unpause the video and we will discuss the solutions together. Welcome back. Let's go through each example molecule and identify the chiral centers. In the first molecule, there is one chiral center, located here. Notice that this carbon is attached to one hydrogen, the propene group, and 2 different sides of the cyclohexene ring. Because the double bond is on one side and not the other, this means that the indicated carbon has 4 different groups and is a chiral center. In the second molecule, there are 2 chiral centers, as indicated on the screen. The carbon atom bonded to the phenyl ring is bonded to a hydrogen, a carbonyl group, and a ring that contains a nitrogen, totaling 4 different groups. The other chiral center shows a carbon bonded to a hydrogen, a nitrogen, the remainder of the ring, and the other chiral carbon atom. Moving on to the third molecule, it contains one chiral center. The carbon atom bonded to the chlorinated phenyl ring, the nitrogen, the carbonyl group, and the other carbon chain is a chiral center. Again, this carbon is attached to 4 different groups, indicating chirality. Finally, the fourth molecule is more complex and contains multiple chiral centers, as indicated. Each carbon atom that is bonded to 4 different groups, including hydrogen atoms and other parts of the steroid ring structure, is a chiral center. Also remember that any carbon that is bonded to 2 hydrogen atoms is automatically not a chiral center, because it would be impossible for that carbon to be attached to 4 distinct groups. Great job analyzing these molecules. Identifying chiral centers is a crucial skill in understanding stereochemistry. Now, let's move on to the next topic, where we will discuss the implications of these chiral centers in more detail. As we discussed at the beginning of this lesson, there are 2 general types of isomers: constitutional isomers and stereoisomers. Stereoisomers differ from one another by the spatial arrangements of the atoms in the molecule. However, to fully understand stereochemistry, we need to recognize that there are 2 different types of stereoisomers. One type is called enantiomers. Enantiomers are mirror image isomers, meaning they are non-superimposable mirror images of each other. We will explore enantiomers in more depth on the next slide. It's important to note that there is another type of stereoisomerism called diastereomers. Diastereomers are stereoisomers that are not mirror images of each other. Examples of diastereomers include cis and trans isomers, which differ in their spatial arrangement across a double bond or ring structure. Before we delve into the details of diastereomers, let's first focus on enantiomers, or mirror image isomers. We will learn how to draw and understand them on the next page. The first class of stereoisomers we need to examine in more detail are enantiomers. As we mentioned earlier, enantiomers are 2 molecules that are non-superimposable mirror images of each other. This means that, just like your left and right hands, enantiomers cannot be perfectly aligned on top of each other. Only chiral compounds, which have chiral centers, can have enantiomers. Achiral compounds do not have enantiomers because they possess a plane of symmetry. But how do we determine what the structure of an enantiomer looks like? That's what we're going to learn on this page: How to draw the structure of the enantiomer of a chiral compound. There are two straightforward methods to draw the enantiomer of a molecule. One method is to draw the mirror image of the chiral molecule. This works because if a molecule is chiral, its mirror image will automatically be the enantiomer. How do we draw the mirror image of a molecule? Imagine placing a mirror next to the chiral molecule and drawing its reflection. Let's go through the step-by-step process for accomplishing this task. Step 1. Start by identifying the chiral center. The first thing to do is locate the chiral center in the molecule. This is the carbon atom bonded to 4 different groups. For example, in the molecule shown, the carbon atom bonded to a chlorine atom, a hydrogen atom, and 2 other groups is our chiral center. Now we can go to the next step. Step 2. Visualize a mirror plane. To do this step, visualize placing a mirror next to the chiral molecule. Imagine the mirror is oriented vertically, so that you can see the reflection of the molecule as if it were looking into a mirror. Now that you have your mirror set up, it's time to go to the next step. Step 3. Draw the reflected structure. Now, draw the reflected structure as you would see it in the mirror. Start by sketching the chiral center in the same position as the original molecule. Then, reflect each of the 4 groups attached to the chiral center across the mirror plane. For instance, if the chlorine atom is on the left side in the original molecule, it will appear on the right side in the mirror image. Similarly, the other groups will swap positions accordingly. Step 4. Verify the configuration. Finally, verify that the resulting structure is a non-superimposable mirror image of the original molecule. Check that the spatial arrangement of the groups is correctly reflected. The original and the mirror image should be identical in terms of connectivity, but different in their spatial arrangement. So one way of drawing the structure of a molecule's enantiomer is by drawing its mirror image. There is another method, however, and it is the one we probably use most often. In this method, we locate each stereocenter, and on the new structure, we invert all of them to the exact opposite configuration. Here it is in more detail. This method involves inverting the configuration at each chiral center. Specifically, if a group is oriented as a wedge, pointing out of the plane towards you, it is switched to a dashed line, pointing into the plane away from you, and vice versa. For instance, if we start with a chiral molecule where an OH group and an NH2 group are oriented as a wedge and a dash respectively, inverting these groups will give us the enantiomer. Both methods effectively create the non-superimposable mirror image of the original chiral molecule. By understanding and applying these techniques, we can accurately draw and recognize enantiomers. Before we conclude this part of the lesson, let's go to the next page and look at some examples of different stereoisomers, and learn how we can classify them by examining their structures. Now let's put our understanding of stereoisomers to the test by classifying the following molecules. We will categorize them as identical enantiomers, or non-mirror image stereoisomers, also known as diastereomers. First, let's look at the pair of molecules on the top left. These molecules each have a carbon bonded to a hydroxyl group, a hydrogen atom, and 2 methyl groups. At first glance, it might seem that these are mirror images, because the hydroxyl groups are oriented differently, one as a wedge and the other as a dash. However, if you closely examine the structure, you'll notice that both molecules have a plane of symmetry. This happens because there are 2 identical groups, the methyl groups, bonded to the carbon in the center, making it impossible to be a chirality center. The plane of symmetry divides the molecules into 2 mirror image halves. Because of this symmetry, the molecules are achiral, meaning they are superimposable on their mirror images. Therefore, these molecules are not stereoisomers. They are identical. Next, let's examine the pair on the bottom left. Here, we have 2 cyclohexane rings with substituents. Each has a hydroxyl group and an amino group, Notice that these molecules are mirror images of each other. As you can see, the hydroxyl and amino groups are arranged in opposite configurations. Because these are non-superimposable mirror images, they are classified as enantiomers. Now, moving to the large set of molecules on the right. Notice the arrows indicating the relationships between these molecules. Let's see if we can identify pairs of enantiomers first. Remember that enantiomers have all their stereocenters inverted to the opposite configuration. Notice that the molecules in the first column meet this criterion. The top molecule has both stereocenters configured as wedges, while the bottom molecule has those same stereocenters as dashed bonds. These two molecules are enantiomers of each other. Similarly, if we look at the second column, we see the same relationship between the two molecules. The wedges are inverted into dashes, and the dashes are inverted into wedges, when moving from one structure to the other. Therefore, these two molecules are also enantiomers of each other. But what about the other relationships? Recall that there are only two types of stereoisomers: enantiomers and diastereomers. Stereoisomers that are not enantiomers are, by definition, diastereomers. Diastereomers are non-mirror image isomers. This means that if there are two or more stereocenters in the molecule, a diastereomer will have some but not all of these centers inverted. We can see this in the horizontal and diagonal relationships drawn on the slide. For example, moving from left to right, we see that the configuration of the methyl group remains the same, but the other stereocenter is inverted. Because both stereocenters are not inverted, the two molecules are not mirror images. Additionally, notice that there are 4 total stereoisomers. This occurs because there are 2 chiral centers, and we learned earlier that the total number of stereoisomers can be calculated using the formula 2 to the power of n, where n equals the number of chiral centers. By examining the spatial arrangements and comparing them as either mirror images or non-mirror images, we can accurately classify these stereoisomers. This exercise helps reinforce the concepts of enantiomers and diastereomers, which are key aspects of stereochemistry, essential for understanding the behavior of molecules in various chemical and biological contexts. This concludes the first part of this lesson. In the next part, we will learn how chirality centers can be described, based on their spatial configuration, and we will explore a systematic method for accomplishing this task. See you in the next video.